Okay, so we talked about like kind of high level, what are LLMs, how do these things even work? And we talked about kind of the anatomy, the structure of an LLM application, which includes some instructions, some outside data, and those instructions and outside data are combined to call an underlying machine learning model to produce an output for the user. And we looked at like kind of a really high level example of how you might build an application like that in the future without needing to understand any of the details of how those different pieces work, using something like the OpenAI Assistance API. And we also talked about how it doesn't quite work yet. So given that it doesn't quite work yet, it's still relevant for us to understand a little bit of how it might happen under the hood. And so for the rest of today, we're going to cover the different pieces of building these LLM apps, starting with prompt engineering. So for us, like for our purposes today, what we mean by prompt is like the text that goes into the language model. And prompt engineering is the art of how we design that text. It turns out that the way you write the text, the structure of the text, and the way that you write the instructions in the text makes a big difference on the language model's output. So we're going to talk about two things. The first is just some high-level intuitions for how you can think about the way that prompts work, using the theme of like thinking of prompts as magic spells, and then we'll talk about some more practical techniques for prompting. So prompts are magic spells. Well, obviously they're not literally magic spells, right? But because language models are not magic, they're just statistical models of text. They take some input text, they run them through a bunch of linear algebra, and then they output a probability of each possible token. So here, like, I think that the next token is likely to be this with this probability, and here's the different weights that I assign to the different tokens. But I think like thinking about an LLM as a statistical pattern matcher is like gives us some bad intuitions of what these things are capable of. So when I think of a statistical pattern matcher, I think of something like linear regression or like Google autocomplete, which is just like, here are the most likely completions of this output. But LLMs today are capable of doing things that really feel like they don't fit into that paradigm. So for example, in Bing Chat, you can, and in ChatGPT as well, you can post an image or you can post some code for some SVG, and you can have the model like can actually describe what that code contains. So to me, like this doesn't really feel like something that would emerge just by statistical pattern matching alone, or at least it's difficult to understand why it would. So Arthur C. Clarke said, any sufficiently advanced technology is indistinguishable from magic. LLMs certainly feel a little bit like magic. And so let's talk about how prompts work with an analogy of magic spells. So prompts are collections of words, and these collections of words achieve effects which sometimes seem impossible, like describing what's in an SVG just by looking at the code. But they only do this effectively if you follow like a bizarre and complicated sequence of rules. And also if you pay too much attention to those rules, that has well-known negative effects on mental health. So let's try to like teach you some of the tricks so you don't have to spend a lot of time stressing about what goes into your prompts. So if prompts are magic spells, then let's try to be more specific. What kinds of spells are they, and what are they capable of doing? And so we're going to break this into 3 categories based on the different kind of ways that these models are trained, which we talked about earlier. So for models that are just pre-trained on the internet, the metaphor we're going to use is that prompts are like a portal into another universe. For instruction-tuned models, so again, models tuned on data sets of where humans answered the question for you, we'll think of prompts as a wish, like a wish for something you want to be true. And then for reinforcement learning trained models, we'll think of a prompt as like a simulation. So first, let's talk about these like pre-trained models, and let's talk about how you can think about these models as creating a portal into an alternate universe. So again, like if you think about the way these models are trained, they basically have taken more or less every document or every like high quality document on the internet, and the model has learned to predict the next token of those documents. And so one way you can think about what these models can do is they can take us to a world in which the document exists, in which some document exists. Like imagine just this immense set of documents. Like think about every document on the internet. And as you pass inputs into the model, what the model is doing is it's trying to say like, let me predict this word based on the most similar document that I can find in my corpus in like a high-level sense. And so these language models are trained on all possible documents. And so in order to actually get the model to do what you want, in order to write a good prompt for a pre-trained model, you can think of prompting as like subtracting possible documents, like taking away some of the documents on the internet and constraining the model to focus on only the document, like the real or imagined document that you want it to be able to follow the sequence of tokens in. So adding tokens to your prompt is equivalent to deleting possible documents, possible worlds that the model might be generating outputs from. And so, initially maybe the language model is thinking about everything from, law to animals to, human affairs. But if you type in David Attenborough, then that constricts the subsets of the documents that on the internet that the model will be trying to follow. Because David Attenborough doesn't talk about law, doesn't talk about clothing. David Attenborough talks about dinosaurs and plants and bugs and stuff like that. And so by writing David Attenborough, you've constricted the model to not considering every possible document on the internet, but only considering documents that seem like they would have the words David Attenborough in them. And then if you write an additional tokens into this prompt, like David Attenborough held up a leaf, then you're further eliminating things like documents that might exist where David Attenborough talks about things like animals or dinosaurs, and instead the model is now thinking of documents that it's seen or imagined where David Attenborough is talking about plants. So of course, like the way that this metaphor fails is that like the model is trying to generate a document that looks like one that it found on the internet. It's not able to actually generate things that like are well beyond the scope of what's possible to have in internet documents. So like the model does not know the cure for cancer because the cure for cancer is not found anywhere on the internet. So a better metaphor for this is it's not imagining like any possible document that you might think of, it's imagining like documents that are similar to other parts of the internet. So if you search for something like documentation for the function, delete shopping cart, or like translating an English sentence, or combining different concepts like Shakespeare and Dungeons and Dragons and Hamlet, then the model will do a reasonably good job at these things because even though there's no document on the internet, maybe, that is Shakespeare's Dungeons and Dragons. I mean, there probably is now, that's probably generated by an LLM, but maybe at the time these models were trained, there wasn't. It's similar enough to documents that it would have seen on the internet about Shakespeare or about Dungeons and Dragons or about Hamlet, that it's able to sort of combine those concepts in a way and produce something that looks like a document that would have existed on the internet if someone had taken the time to write it. So that's kind of high-level intuition for how you can think about prompting in the world before instruction tuning, which is like the model, what the model's good at is like generating data that looks like documents on the internet. It's not able to produce new information, but it's able to combine information from very disparate documents in novel ways. And so you can get it to do things like combine concepts to produce documents that don't exist but look like they could have existed. Instruction tuning kind of changes that, right? Because now the model is not just trained on documents on the internet, it's also trained on these instruction following data sets. So you can think about like what these models are capable of as like wish fulfillment. So models will, with instructions, you can, rather than needing to kind of prime the model to think about going to a world where the document that you want to exist might have existed, instead with instruction you can literally just ask for what you want. So if you ask a question, if you just describe the output that you want, then the model does a reasonable job of producing it. So one kind of like corollary of this is you have to be careful about what you wish for. Right? Like just like, a lot of times if you wish for something from a genie, you get something that is not exactly what you really wanted. Just like that, in instruction following, it helps to be very precise about exactly what you're looking for, because the model can't read your mind, right? If you ask it to write a story, it doesn't know what you want that story to be about. It doesn't know what characteristics you want that story to have. It will do that, but it might not actually produce the output that you want. So it's important to learn the rules that this particular genie has for how it follows instructions. And we'll talk a little bit more about this in a second. But some of the things that are really helpful are, rather than assuming a bunch of knowledge from the model, rather than assuming that it knows what specific terms mean, or it understands the world in the way that you want it to understand, instead give it simple low-level patterns, give it simple rules to follow, and it does pretty well. Rather than having like a long task, which includes like high-level concepts like the idea of a common sense question, the idea of long, interesting, and complex questions, goals that relate these concepts like AI and machines, things that the model might not understand from its simple instruction training. Instead, you can reframe a task to be really concrete and really simple. Like use words like what may happen, will, or why might. This is unambiguous and it's easy for the model to interpret because it doesn't require it to have a bunch of background knowledge about the world. This is one of the most effective ways to get models to do what you want. Are we seeing text here? Okay. Another pattern here that you can follow is these models tend to do well with things that are itemized, with things like lists. So rather than like writing long descriptions with lots of sentences that contain information that is important for the model to understand, just like if you're describing something to a human, like someone who's busy or distracted, oftentimes it helps to just break these things into small chunks, like lists, and provide those things. In the first example here, the raw task, they show a bunch of inputs that are provided as one sentence after another: do this, don't do this. Instead, the model performs better if you break these things out into bullet points and say like, do this, and do this. One other trick that helps a lot is oftentimes it's easiest to describe things as like, don't do something. Don't answer the question if you don't know the answer. Don't like respond in full sentences, only use short phrases. But these models tend to perform a little bit better if you reframe those things as positive things, like things the model should do, even if it's a little bit more awkward to phrase them that way. And the intuition for why this is true is because it's kind of like, if you tell someone to imagine an elephant, or tell someone not to think of an elephant, right? Like, what is the first thing that they're going to think of? Just like that, models, if you put a word in their context, even if you're telling them not to do it, now they're primed to think about the world in which that word exists, which will make them, in some cases, more likely to do it, even if you explicitly told them not to. Maybe that's actually one of the reasons why the prompt I showed before wasn't working. It's worth saying that, I think a lot of these rules are becoming less and less relevant as models get more advanced, but it's still, if you're having trouble getting the models to do what you want, it's a helpful thing to try. Another important piece of context to understand about these instruction-tuned models is that if you think back to how the data was created, right? It's OpenAI and companies like it, they gathered a set of instructions and then they paid people on the internet to follow those instructions and try to answer the question. So the people that are producing those answers are annotators, right? They're not necessarily subject matter experts. They're not your team. They're not someone who understands the problem well initially. They're someone who maybe has never done this task before and needs to do it. And so one way to make these models more successful is to treat them like annotators. Treat them as if you were hiring someone on the internet to do the task. Oftentimes what that means is be very, very, very specific about what you want them to do and be as unambiguous as you can and not assume any specific background knowledge that these people have. So third kind of metaphor that you can think of for prompt engineering when you're working with a reinforcement learning from human feedback tuned model, like a modern ChatGPT, is a prompt can create a magical artificial agent. And one sort of mental model you can have for that is models can take on personas. So a lot of times what can be helpful with these models is you can tell them what kind of person do we want to simulate? What kind of agent do we want you to simulate? So if you looked at people's prompts on the internet, oftentimes they'll start with kind of this like very obscure sounding phrase like, you are the world's best grammar teacher, or you know, you are an incredible coder, or you are, you know, a sassy but factually accurate cooking instructor. And so what you're doing is you're basically telling the model what persona you want it to take on. So you're describing the type of agent, the type of person who would produce the kind of answer that you want to produce. So, you know, you can, like, one sort of effective technique for these reinforcement learning tune models is to try to describe, like, the personality, the attributes that you would want a person who would answer this question to have. And the models are able to use that to kind of zone in on the type of answers that you want them to provide. So, you know, as LLMs get really, really good, they become more and more universal at simulating things. So the reason why this works is because as you ask the model to compress more and more information, one of the most effective ways that it can do that is by learning an internal representation of the simulation that might produce that text on the internet. So if you want to write like Paul Graham, then in order to describe that to someone who doesn't know who Paul Graham is, you would need to write tons of rules and give lots of examples and just really pass a lot of information to that person for them to be able to reproduce that style of writing. But if you are Paul Graham, or if you are someone who understands his writing style perfectly, if you're able to simulate Paul Graham, then just saying write like Paul Graham is enough to describe a very specific style of writing. And so language models, as they compress more and more of the internet, in order to represent the information on the internet compactly, they learn these internal representations of things that you can get them to reproduce by just describing the type of thing that you want them to output, or the type of person who would output the type of thing. And humans are like one thing that you might simulate, and one effective thing to try to get your prompts to simulate, but not the only one. So again, like kind of corollary to the point in the previous section, but you know, it's important to think about like since the reason why this works is due to the way the models are trained, there's a limitation here. So we're only able to simulate things that look like data that they have in their training set. So if we ask the model to, you know, say like, you are a superhuman, super intelligent AI, will the result be that you will have a super intelligent AI on the other side? Well, no. There's no super intelligent AIs in the data set to learn to simulate. So the thing that you're asking the model to simulate needs to be something that it's seen in its data set before. So asking it for, you know, a New York Times journalist, or like a math teacher, those are things that the model will be able to simulate effectively. But you know, anything that it's not seen on the internet before, maybe not so much. So the interesting thing, though, that happens if you ask the model to simulate a super intelligent AI is that it doesn't become a super intelligent AI, but it becomes like a fictional super intelligence. It becomes like the super intelligences that people have written about in the past. And so like what happens if you do this, or what happened if you did this before, like a lot of the more recent like reinforcement learning training, is that you get models that start to exhibit really creepy behavior, because that's the way that super intelligences are described in fiction. Another limitation is like, okay, how well should we expect this to work? Like how good is this simulation going to be? Are we seeing the slide advance here? Okay. So like some kind of mental models you can have in mind are that language models are good at simulating things that there's a lot of data for on the internet. So a lot of times people write things on the internet that they thought about, but usually not more for than like a few seconds. So models are really good at simulating what humans thought about for a few seconds. Models are also really good at simulating like people on Reddit, because they were trained on a lot of data that came from people on Reddit. They're not often as good at like replicating human thinking that takes a long time, like something that you thought about for hours, a detailed plan and reasoning. You know, because people don't really put much thought into things that they put in the internet oftentimes. models are really good at simulating like common fictional personas. Like if you ask a model to be a character from like a story that people have written a lot about, a character from Harry Potter or something like that, it'll do it well. And then for other things, like for processes that are maybe harder to follow, like a calculator or a Python kernel, model can actually do a surprisingly decent job at simulating those things. But that's probably not like the most effective way to get the model to use tools like this. And we'll talk about a more effective way to do it in a little bit. And so, you know, where possible, you want to, like, rather than having the model do the things that it's weak at, you want to have it do the things that it does well, and then replace the weaknesses with the real deal. Like, replace it with the actual human thinking or with the actual live API call or Python kernel. And we'll talk about that in when we talk about how to augment language models. So takeaways on kind of like the intuition front. Mostly, you can think of pre-trained models, like especially models before instruction fine-tuning, as just like being really good at generating documents that look like something you might find on the internet. After instruction fine-tuning, models gain the capability to where you can just ask it for what you want. But the key is you have to be really precise about what you want. Otherwise, the model will just imagine what you want, and that might not be the exact thing. And then like one other technique you can use for prompting models is you can treat them as agent simulators. You can describe the type of agent that would produce the result that you'd want to produce. And oftentimes that makes the model better at doing its job. But it doesn't do this equally well for all different types of agents that you might want. I'll pause here and see if there's questions, and then we'll talk about like some of the more practical side of prompt engineering. Yeah. You can, and so this is one of the best ways to get language models to do what you want is to give them space to think. And so and we'll talk more about how to do that in a second, but the intuition there is like, you know, the model is predicting the next token. And so if you ask the model a really complicated question, and you expect it to just spit out the answer, then the model has to be able to like perfectly understand the question and know what the answer is right away. To the point where like it gets it right the first time. If you instead ask the model to like think about the answer and then answer the question, then it's able to produce a lot of tokens. And so even if the initial answer is wrong, it's able to self-correct oftentimes. Yeah.
Just a clarification, you mentioned about pre-trained models are mostly AU document generation. What does AU mean there?
I don't remember.
Okay, is it a typo or something?
Did anyone catch that? Yeah, I forgot what that was. But just think about it as like documents on the internet. Alternate universe, there we go, yeah. Cool. Okay, let's talk about some prompting techniques. So one thing off the bat is that like prompt engineering, unfortunately, is mostly just like a bag of tricks. It's a bunch of stuff that kind of works, that people have discovered empirically works. It doesn't always like make sense. Like you hear the term prompt engineering and you think of like, this is gonna be an engineering discipline, like a lot of the other engineering disciplines that you've probably learned. It's not. It's really just like a bunch of random things that if you know these things, your prompts will be more effective. That's why I wanted to talk a little bit about the intuition side of things, because even though it's a little bit hand-wavy, it does help tie some of the things that work together a little bit as you build like a high-level intuition for how this is connected to the way that the models were trained. And so we're gonna like cover this in two steps. The first thing is we're gonna talk about like some of the weird things to watch out for, and then we're gonna talk about like what seems like is becoming an emerging playbook for how to do prompt engineering effectively. So first, like some unfortunately painful things about dealing with prompt engineering. And the first is that like few-shot learning, like was described in the original GPT-3 paper, is not actually a very good model for how to get these models to do what you want. So in the GPT-3 paper, the paper was called Language Models Are Few-Shot Learners. And the idea was like, they discovered that, if you'll recall back to like a slide from this morning, if you provide models with a handful of examples of the behavior that you want, these large language models, these 175 billion parameter models, are able to generalize to the n+1th example surprisingly well. But unfortunately, that model for like thinking about what these models are, that mental model for thinking about what these machine learning models are doing hasn't held up very well. So if you want to translate from French to English, one way that you could do that is you could provide the model with a handful of examples of the English phrase and then the corresponding French phrase, and then ask it to repeat that example. But it turns out that if you craft your zero-shot prompt effectively, like if you give the model good instructions about what you want it to do, sometimes that can do just as well, if not better, as providing the model many examples of what you want. So if you instead provide a French phrase and then ask the model to simulate being a masterful French translator, then for modern models that can work just as well as providing a bunch of examples of translation. That being said, models do struggle to move away from their training data. So if you one challenge of this few-shot model is if you provide a handful of examples, you wouldn't expect the model to do the same thing well on another demonstration that looks really different from the ones that you gave it. And so these limitations are getting less and less as models get more capable, but it's still like a limitation to be aware of. One other kind of like nasty bit to be aware of as you're doing prompt engineering that again is getting better and better, but it's still important to be aware of, is that when you read something like hello world on the left, it's like you're able to make sense of those characters in a way that you see two words there. One sort of detail about how these models are trained is that each of the characters, each sequence of characters are converted into tokens. And these tokens are like, you can think of them as representations of words. But there is no like fixed set of words in the English language or any other language. There's always like other phrases or sets of characters that have meaning that the developer of the model might not have thought of. And so if you basically take this hello world phrase and you deterministically change each of the characters in a way where you could reverse the meaning back, then the model, rather than seeing this as two words, now we'll see it as 6 different words because of the quirks of how the model's tokenization is created. And so that means that depending on how you depending on how you the specifics of how you write the inputs, the model can have very different effects. And so one of the most famous examples of this in early GPT-3 was that GPT-3 was really, really bad at simple tasks like reversing words. So if you tried to get the model to reverse reverse a word like alphabet or encyclopedia, then it's basically it's not able to do that, even though that's a really simple task for humans. But the core reason for this turned out not to be a limitation of the reasoning of GPT, but a limitation of the tokenization. So instead of so when GPT sees the word encyclopedia, it sees a single token, like a single concept that's represented in the model. And so it's hard for it to reverse that because it doesn't, that's not a thing that it associates with the word encyclopedia. But instead, you can make GPT-3 see not the whole word, but the individual letters, just by adding a space between the letters. And if you do that, then it turns out that each one of those letters becomes its own token. And so the model sees not one word, but a sequence of tokens. And when it sees the sequence of tokens, then it's able to actually reverse those because it now sees many things and it can just flip the order of them. So this has been mostly resolved in more recent models like GPT-4. And so it's not something that you might encounter day to day if you're using exclusively models like GPT-4, but if you use open source models or you want to use kind of smaller or older models for the purpose of cost or anything like that, then this is something that you might run into. And I think I didn't include a link here, but OpenAI has a great tool on their website that can allows you to see how different phrases of text are tokenized. And so if you're concerned about tokenization being a limitation of your prompts, then you can paste the raw text into that tool and see the tokens that their models recognize. So that's kind of like some of the like important but unfortunate like details of prompt engineering that you have to know about. Now I want to talk a little bit about a playbook for how to do this well. And there's 4 different components to it. The first is, it tends to work really well to operate, rather than like on unstructured text, to operate on text that's more structured. And so we talked about that a little bit in the previous section of like breaking instructions into bullet points or enumerating them, but you can add even more structure than that. So you can like ask the model to use a very specific format for its outputs. You can provide markdown text, you can provide code snippets. And the model, and prompts tend to do better the more structure that you put into them. Another technique that works really, that is like super critical to understand for prompt engineering is, one challenge that models have with following instructions is that as instructions get longer, like you start to see the model like forgetting about parts of the instructions or ignoring parts of the instructions. So if you have like, at Gantry, we've been working on a prompt to do really complicated tasks, which is detecting hallucinations. And in order to detect hallucinations, you need like, there's a whole bunch of details that you need to know about what a hallucination is, what counts, what doesn't count. And so we ended up with this really long prompt. And the problem we were seeing was that like the model was not doing what we saw in the instructions, because it just got, it would sometimes follow the part of this part of the instructions, and then sometimes it would kind of forget that this phrase was like further up in the instructions. And so if you start to see that, like if your instructions, like you want your instructions to be detailed, but if they start to become too detailed to the point where the model doesn't follow them, then you can start to decompose your prompt into multiple steps. And so like one way to do that is within the prompt itself. Like you can specify the steps that you want the model to follow. And as that becomes like too much detail for the model to handle, you can literally divide it into separate prompts. Like you can just have one prompt that follows one part of the instructions, take that output and pass it into another prompt that has a similarly simple but different set of instructions. And you can add like this sequential nature to your prompts and form chains, which allows the model to like follow more and more complex instructions. So one way that you can think about decomposition of prompts is like you're basically like adding a manual reasoning step to the model. So like a common type of decomposition would be to say like, okay, great, your job is to, what we saw in the previous example, to reverse a set of inputs. So first, I want you to add a set of spaces in between each letter of the word, and then I want you to reverse the inputs. So we've told the model like, this is the logical sequence of simple actions that we want that you should follow in order to do the thing that we want you to do. So we've taken the reasoning away from the model. We've solved the reasoning problem for the model, and it just has to execute on a simple set of tasks. It turns out that you can try to automate this process of adding reasoning. And there's a few different ways of doing that. It's like one way is you can ask the model whether it should answer follow-up questions. But I think by far the most common, let's see. Yeah, I think like by far the most commonly done, most common way of doing this in practice is just by asking the model, like telling the model that it should think about the answer before it produces it. And so oftentimes you'll see this phrase in the prompt as like, let's think by step, or take a deep breath before you answer the question, or like write out your reasoning and then produce an answer. The exact phrasing matters a little bit, but not so much. The core idea is like, you're telling the model that before it answers the question, it should first think about the answer to the question. And that doesn't always perform as well as like telling the model the reasoning that it should follow, but for complicated tasks, it usually performs better than just asking for the answer directly. Because the model has time to break the question into pieces and answer each of those simple pieces before coming to its final answer. A similar, like a corollary of this is you can ask the model to answer the question, and then you can ask it, and then you can like basically provoke it into telling you why that answer is wrong. So if you ask the model to like answer the question, and then you say, hey, next you should review your answer and find problems with it. The model is like often able to point out flaws in an answer that it gave even just a moment before. And that can lead to higher quality answers. So asking the model to criticize its own answer and then revise it is often a way to improve the accuracy of your answers. And then a final way that can help improve the quality of the final answers that you get is to ensemble. And what that means is, rather than asking the model to answer the question once, instead ask for many answers, like run the LLM many times. And then instead of taking the single answer that one model gave, look at all those answers together and pick the one that's the most common. And that can improve the accuracy quite a bit as well. So in order to get a really, really high quality prompt, like a really accurate prompt on a difficult task, you can combine all of these things as well. So you can use chain of thought, decomposing the task into different subtasks. You can ask the model to think step by step, and you can ensemble it. And if you combine all those tricks together, then you can get very, very accurate prompts. And in fact, combining those tricks together leads GPT-4 to perform better than most human annotators at most annotation tasks, which is problematic if your goal is to collect a lot more training data than already exists today. But it's really good if you're trying to apply these expensive models to difficult problems. So important trade-off here is that each of these techniques come at a cost. Having a slide issue again, let's see. There we go. So few-shot chain of thought is, again, kind of asking the model to follow a sequence of steps. Usually add some latency and add some compute, because you're having the model do more than just produce the output token. Similar thing for zero-shot chain of thought, where you just ask the model to think step by step. But usually it's a little bit lower cost and latency because you don't need to introduce as many tokens to the input to describe the specific reasoning that you want the model to follow. All you have to do is think step by step, and the model is able to add some reasoning. Explicitly decomposing the prompt into multiple steps introduces additional latency and compute for a similar reason as few-shot chain of thought. Ensembling doesn't really introduce any latency because you're running all these things in parallel, but greatly increases the compute because you now need to run the model many times. And then self-criticism is you take a pretty big hit to latency because you need to answer the question once, criticize the answer, and then write your revised answer. So it's basically more than twice as expensive as just producing the answer itself, or twice as long. And so depending on your latency requirements, you can apply different ones of these techniques. If you're doing a task where accuracy is paramount, but you don't need an answer very quickly, you can break this problem down into very small chunks. You can have each of those chunks be run by a separate LLM. You can ensemble all the results and combine them using a lot of logic that requires many calls to the LLM. If you need a system that you can interact with a user in real time, if you're building a chatbot or something like that, then usually you want to avoid as many of these things as possible, because oftentimes it's better for a user to get an answer quickly, even if that answer is less accurate, than for them to have to wait a long time for something that might be more accurate. So a few additional practical tips that I've found when doing prompt engineering. So again, you can think of prompting as writing instructions for a human labeler. And so you really want to be painfully precise and clear. It's not so much describing this to yourself or to a friend. It's you want to describe this in a way to someone who has never heard of your task or thought about your problem at all before. Don't assume that the model is an expert in the thing that you want it to do. Another kind of thing to watch out for is that different models have different conventions for prompting. So one practical example of this is OpenAI does really well with data that is markdown formatted, but not every open source model handles markdown formatted data well. And so if you write a prompt for one model, don't just assume that it's going to work equally well for another model if you're trying to switch from OpenAI to open source or change between providers. For OpenAI prompting, I find that keeping as much of the logic as possible in the system prompt tends to be more effective than having it be in the user user part of the message. We talked about this a little bit. Models struggle with long instructions. And so decomposing into multiple model calls tends to be critical as the instructions get really complicated. And one other corollary of this is like if you have any instructions that are like super critical, like formatting the output, if you always need the output to be JSON formatted or something like that, then put it at the end. And in fact, like oftentimes what I'll see is, or one thing that can work well is like if you have a model that's having a conversation with a person and you always want it to respond in a certain format, then just remind it at every single turn in the conversation, don't forget to respond in this specific format. Models tend to prioritize instructions that are towards the end. And then like one other kind of practical thing that I see people get wrong a lot is like generate the chain of thought first before you answer the question. So sometimes I'll see people write prompts like, you know, tell me what the answer to this question is and think step by step. And so then sometimes the model will say like, the answer is this, and here's my reasoning. That's backward because the model has answered the question in a way that's fast without giving it much time to think, and then it's trying to justify its answer. Instead, what you want them to force the model to think through the answer first before it says what the answer is. And that tends to work a lot better. So we talked a little bit about critical instructions like formatting. And I find like one of the places where people get tripped up on prompt engineering a lot is producing structured outputs for LLM calls. Like how do you get the model to always respond in the exact same way, like to follow a specific JSON format or something like that. So just ask is a pretty good baseline. You can write something in your prompt like always reply in JSON with the following format. And generally speaking, for something like GPT-4, it'll do a decent job at following those instructions, but it won't be super consistent, or it won't be 100% consistent. And so if you want better guarantees on the model outputs following a specific format, you can try some of the following things. So OpenAI has a mode called function calling, which is the way that OpenAI encourages you to use tools. And we'll talk a little bit more about that in the afternoon. But one thing to know is that like OpenAI function calling is not only for pulling in external information. You can also use OpenAI function calling and their like new JSON mode that got released last week to get the model to more consistently follow a specific output format, even if it's not calling a function. So there's some external libraries that help a lot with this. The one I like best is called Instructor, which just produces, like, has an ergonomic way of specifying the output format that you want for the model. And there's another library from Microsoft called Guidance that helps with this too. One of the reasons why you might consider eventually moving to open source LLMs or fine tuning, which are things that I typically don't recommend doing at first, is because that's either of these things are will allow you to have much more guarantees about what the structure of the output looks like. So if you have an open source LLM or generally an LLM where you can look at the probability of all the tokens, then you can constrain what the model samples to always produce things in the format that you want it to produce. It's impossible to do with a Anthropic or OpenAI API because they just don't expose that to you. But if you have full control over the model, you can just say hey, for the first token, just always sample an opening bracket. Or for tokens 3 through 5, don't actually sample. Just use this specific text that I told you. And then for tokens 6 through 8, then choose between these two options. Don't choose from anything, just choose A or B, or true or false. And so that's the kind of thing that you can do with open source LLMs that you can't do with closed source LLMs. Fine tuning, I think one of the main applications I see of fine tuning, I think people reach for fine tuning too early, oftentimes with LLMs, before they've really tried to solve the problem with prompting, which is usually a much easier way of doing it. But one of the good reasons to use fine tuning is if you're having trouble with consistent output formatting, because this is something that fine tuning is able to do pretty easily. Okay, so let's try to apply this to a not so practical problem, and which is trying to test whether language models have theory of mind. So this is a big controversy when some of them, ChatGPT came out. Theory of mind is a type of agent simulation. So a simple example is give a scenario where you have to understand what the person in that scenario would be thinking. So here's a bag filled with popcorn. There's no chocolate in the bag, but there's a label in the bag that says chocolate and not popcorn. If a person finds the bag and she'd never seen it before and can't see inside of it, then what does she think is inside of it? So in order to answer this question, you have to understand what is this person's model of the world? So in this description, the person sees a bag, they see that it says chocolate on it. They don't know that it has popcorn in it, so they would think it has chocolate in it. But on the other hand, if the bag is made of clear plastic, then they wouldn't be confused by the sign that says chocolate. They'd see through the bag and they'd see that it contains popcorn. So when modern language models first started becoming popular, this is like one of the things that critics pointed to as a reason why these systems are not actually that intelligent. They don't have theory of mind. They can't answer questions like this because they get confused by the wording. They don't have a mental model for what the person is actually doing. So, I think when this has like been true over and over again in deep learning, but when curmudgeon-y people tell you what language models can't do, it's usually a good idea to be skeptical, because the more specific you are about what they can't do, the more likely it is that they're going to be able to do it very soon. So let's try to like make a language model actually solve this theory of mind problem. So one thing that we can do is just fiddle with the phrasing. So like it turns out that in this example that people were pointing to as, oh, this is proof that language models don't have theory of mind, if you just swap the phrase Sam reads the label to Sam examines the bag, then the model gets the answer right. If you read the label, you might think that there is chocolate in there, but if you examine the bag, then you would know there's popcorn. Another thing that you can do to make this more consistent is, even if you ask it to read the label, if you add some reasoning, like add a reasoning step to this, so you ask the model to think step by step before it answers, then the model will get the answer right, because it realizes that if you read the label and it says chocolate, you actually have to go one step further and think about what Sam would do after they read the label. Another way that you can solve this problem is you can actually directly model agents in dialogue. So you can ask the model to, instead of just answering the question, write a dialogue between Sam and a friend, and see if that gets you to the right answer, which in this case it does. So this is not really like just to say that language models definitively have theory of mind or anything like that. I think it's like whenever you make a claim about something a language model can do, you always have to make it in the context of how you're actually trying to solve the problem, like the specifics of the prompt. So I'm not saying definitively language models have theory of mind, but this is just an example of how applying best practices of prompting can take something really hard, something that for a while people actually thought was impossible to do with language models, and turn it into something that's well within the capabilities of models to do. So takeaways from this section. Prompts are super fiddly. Like you have to, oftentimes changing one word or one phrase in a prompt changes it from working to not working, or not working to working, which can be really frustrating to work with. But there is an emerging playbook that involves things like structuring the prompt and asking it to think step by step, which generally will get you a good chunk of the way there. And to go from something that works a reasonable amount of time to something that works really consistently, oftentimes is less about knowing all the tricks, and it's more about experimentation. And we'll talk this afternoon about how to experiment in a more structured way through evaluation. Any questions on prompt engineering?
Okay. I really like the ensemble concept. That's cool. You could see like automating that even and getting a bunch of answers back. Can you ask it to pick the best answer?
You can, yeah. So oftentimes, like the as you explore this idea to the limit, you end up building these chains of reasoning where some of the reasoning is like predetermined by the human. So like I might say my predetermined reasoning might be I want 10 models to answer this question with, or I want to make 10 parallel calls to GPT-4 to answer this question. And then some of the reasoning might be adding another LLM on top of it. So like a totally deterministic way of doing ensembling would be to say like, great, I'm gonna ask the model to answer the question 10 times, and then I am deciding that I want the answer that is the most common, that to be the final answer. But there's no reason why you can't ask a language model to apply that reasoning on top of it. So you could say like, I want the model, like you could produce 10 different answers, and then you could ask another model to read the 10 answers and respond with the one that's the best. And so that type of like applying LLMs to multiple steps in the pipeline is pretty common, especially with information retrieval, which we'll talk about in a bit.
Hello. I had a question about hallucinations. I know we talked about it a little bit.
Yeah.
And in my experience, they're mostly solvable just through prompting, but sometimes in rare cases it still happens. And I'm just curious if you have any suggestions besides prompting. I know one thing that might work is, I think what you called self-criticism, which is just asking another LLM to double check if hallucinations are happening. But I'm wondering if there are any other patterns that you would suggest looking into.
Those are the main two I see, yeah.
All right, cool, thank you.
Yeah.
When you have multiple prompts, so I'm just thinking in terms of engineering this, right? So can you actually run it in parallel so that you kind of speed up the whole process?
So it depends on how you construct the pipeline. So if you do something like ensembling, where you ask the model to answer the question many times, you can run that in parallel because each of the copies of the model needs access to the same information. But if you want to do something like self-criticism, or if you want a model to look at the 10 answers that the model gave and choose the best one, then those just like logically have to be done sequentially, which adds a lot of latency. And so a lot of these techniques are things that don't work in every circumstance. If you're very latency sensitive, then your toolkit to solve these problems is much more limited. But if you can afford to spend a lot of money and a lot of time to make many calls in sequence to the language model API, then you can get more accurate answers through things like self-criticism. Cool. I'm just going to talk a little bit about like sort of forward-looking perspective on prompt engineering before we break for lunch. I think there's kind of like a question that's been floating around like, is prompt engineering here to stay? And I think a lot of this maybe was triggered by, at one point, Sam Altman did an interview where he said he thinks that prompt engineering is like not a real thing. It's like not a thing that people should study because it's going to go away as models get better. My perspective is that like, I think there's two ways to think about prompt engineering. The first is thinking about prompt engineering as we described it before as like a bag of tricks, right? There's like, you need to tell models to think step by step. You need to format things in a certain way. You need to provide structure in the prompt. That's probably not here to stay. I mean, I think even in the past year since ChatGPT has been released, like prompt engineering, the trick part of prompt engineering is way less important than it was. In 2020, 2021, in order to get models to do the thing that you wanted them to do, you often had to do like quite a bit of prompt engineering to get the model to imagine the world in which the document exists. Since these models have been like much more heavily instruction tuned and RLHF tuned, most of the time just ask works reasonably well. But there's another way to think about prompt engineering, which is to think about prompt engineering as task specification. So how do you precisely define exactly what you want the model to do when it's faced with novel inputs? And to me, that piece of it seems pretty unavoidable. Because even if you had AGI, like if you had your smartest friend and you wanted them to do a task they'd never done before, you'd still have to describe to them what you want. Otherwise, they might do something in a way that makes sense to them, but isn't actually what you asked for. So that piece of it seems unavoidable. So what will prompt engineering look like a year from now when maybe the bag of tricks is gone, but the task specifications still exist? And I want to cover like a few different sort of emerging research fields, like different visions for what automated prompt engineering might look like. The first one you can think of as prompt compilation. And so there's a library from research team at Stanford that is kind of pushing this idea forward that's worth checking out if you're interested in this stuff, called DSPY. And the idea of prompt compilation is that like, just like when you train a model or fine-tune a model, you provide a data set of input-output pairs. And then, in the case of fine-tuning, you perform additional gradient descent, additional training of the model to get it to do what is represented in those data points. You can apply a similar technique where you provide, example inputs and outputs, and you run optimization to determine what the correct behavior is on new outputs without necessarily doing like a formal fine-tuning process. And so these are different forms of optimization that you can use given like a small amount of labeled data to get the model to do something that looks more like what is in those data points. And so the way that this works is, you have a very high level description of the task that you want, like a very generic description of the task, and then you provide some examples to an algorithm, and then that algorithm searches over the space of prompts. Like it tries a bunch of different prompts in order to find a prompt that performs well on the task that you defined by providing these input-output pairs. So that's like one kind of vision for how prompt engineering might evolve is rather than needing to write the specifics of the prompt yourself, maybe you just provide examples to the model and it's able to find the prompt that works the best for those examples. Another like kind of vision for how this might work is like what I would call prompt expansion. So if you've ever used, how many of you use like ChatGPT with the DALL-E component to it as well, like to generate images? Yeah, a handful. So if you notice, like I can write something really simple, like draw an image of an AI class, and the model produces this like beautiful, detailed output. But what's going on behind the scenes is that GPT-4 is taking my input and it's transforming it into something that is much more specific, that follows the rules and best practices of prompt engineering for the image generation model DALL-E. So I draw an image of an AI class. The way that GPT-4 interpreted that is this much more detailed prompt on the right, that it was the raw thing that was passed to DALL-E, because DALL-E performs well with prompts in this format. And so in a similar way, what you could imagine is a meta prompt that understands all of the rules and best practices of prompt engineering, where I can just write the prompt the way I wanted to write it, and then the model will interpret it for me and pass that transformed version into the model to cause it to do the right thing more effectively. Yeah. Yeah, exactly. So prompt engineering. So I think like the third vision for this is a prompt engineering copilot. And I think, so the first step here is you describe, it says like, hey, I want to help you build a new GPT. Like, what would you like to make? And then I write a description. So I want a bot for helping answer questions about prompt engineering. Then what you get is you get like, I can write something to this bot, like how can I improve this prompt for better results? And the bot will answer. But what's happening behind the scenes is that the model has taken this initial set of instructions and it's expanded it into this longer set of instructions that you see on the right, which is the instructions for like how the bot works. So that's really similar to the previous example of prompt expansion, right? Like I took a short description of the bot and the model compiled this into a longer description that it uses to actually answer the questions. But where I think like this expands on that vision is that the limitation of that technique is that like the model can't read your mind. The model doesn't know what it means to be a bot for helping answer questions about prompt engineering. It can imagine that. It can imagine what that means, but that's only going to be one possible interpretation of the phrase that I wrote. And so what's interesting about this is it puts it in more of a conversational paradigm, where the model, the assistant, the prompt that you're interacting with has a chance to ask you questions to clarify your preferences. And so you can think about this as a very, very early version of a prompt engineering copilot, where like, imagine if you had your smartest prompt engineering friend who doesn't know the task that you want to do, but knows how to do prompt engineering really well, and can sit with you and answer questions to elicit your preferences, to compile it into a more and more specific version of the instructions that you want the model to have. And so I think the direction this is going, like, I think what it means for prompt engineering to be automated is that like a combination of these three things, where you have prompts that help take away the sort of mechanical part of prompt engineering. You have ways of taking human examples and human feedback and directly integrating those into prompts. And you have a copilot who sits with you and asks you questions to elicit your preferences, and ultimately leading to like a more specific prompt for what you're trying to do. So I think a year from now when we teach this class, maybe we won't need to teach prompt engineering at all, because we'll be able to just do all this automatically. So one thing that's underlying this is that better prompt engineering, like in order to do this effectively, at the limit, applying these techniques and these tricks only goes so far. Because like if you like you're limited by the number of things you can try because there's only so much time in the day and there's only so much ability that you have to tell whether it's working. And so to get really good at prompt engineering, more important than knowing all of these tips and techniques is knowing how to carefully evaluate whether the prompt that you wrote is actually doing the thing that you want it to do. And so that's one of the things that we'll talk about after lunch. So also left some resources here about like other places you can go to learn more about prompt engineering if you want to dig deeper into this. And yeah, we're a bit behind schedule, so let's take a lunch break and come back at, I don't know, maybe 12:45 or so.